Hello everyone, it's an honor to be here at the third International Conference on Civil Engineering and Intelligent Construction, ICCEIC 2025. I'm Dr. Ahmad Modhej, and today I'll present our latest work on hybrid damping systems designed to significantly improve the seismic resilience of building structures. These systems combine the best features of viscoelastic and plastic damping technologies. Our talk today is titled Development and Experimental Validation of Novel Visco-Hyperelastic and Viscoplastic Dampers for Seismic Energy Dissipation in Building Structures. We'll go through the motivation behind our research, the materials we developed, and the results from experimental validation and real-world application. The need for better seismic protection is ever growing as we face more frequent and intense earthquakes. Conventional damping systems often fail to maintain efficiency when subjected to high or repeated deformation. Our research addresses this challenge by developing hybrid dampers that combine viscoelastic and plastic energy dissipation mechanisms for improved performance across a wide range of seismic excitations. Here we categorize damping systems into three main types: velocity-dependent devices, for example, viscose and viscoelastic dampers; displacement-dependent devices, for example, yielding and friction dampers; and hybrid systems that integrate both velocity and displacement responses. Our hybrid systems, the Visco-Hyperelastic damper (VHD) and Viscoplastic damper (VPD) are designed to combine the strengths of both. In hybrid damping systems, viscoelastic and plastic mechanisms work together to handle the entire spectrum of seismic forces. The result is stable hysteresis loops and efficient energy dissipation across various loading conditions. Our two primary systems, VHD and VPD, achieve this synergy. A key innovation in our dampers is the High Axial Damping Rubber (HADR). Unlike traditional rubber, HADR is engineered to dissipate energy axially, making it far more effective under large strain conditions. It's composed of natural rubber, carbon black, zinc oxide, oils, and resins, all chosen for high durability and excellent energy dissipation properties. The Visco-Hyperelastic damper VHD combines two concentric steel rings with a viscoelastic rubber core. At low levels of excitation, the rubber core provides viscoelastic damping. At higher amplitudes, steel rings yield and both plastic and plastic deformation occur to dissipate energy. This allows the VHD to handle a wide range of seismic events efficiently. We developed a finite element model of the VHD in Abacus to simulate its performance. The model uses a visco-hyperelastic material model for rubber and an elastic plastic material model for steel. Our numerical results are validated against experimental data, showing excellent correlation and confirming the system's reliability. Here we can see the numerical results for energy dissipation. At low displacement, less than 4 millimeters, the system behaves viscoelastically. At high displacement greater than 4 millimeters, the steel yields and energy dissipation increases to 99%. This hybrid design ensures optimal damping across various seismic scenarios. We performed a parametric study on a one-bay, one-story frame using Abacus, analyzing the impact of different damper parameters. Rubber material. Higher damping leads to reduced roof acceleration and displacement. Steel thickness. Thicker steel plates improve overall stiffness and damping. The optimal balance was found with 60 Shore rubber and 4 millimeters steel plates, which reduced displacement by 67% and acceleration by 54%. Next, we move to full-scale experimental testing of our dampers. These tests were conducted under cyclic loading conditions with displacement ranging from 6 to 24 kilonewtons and frequency from 0.33 Hz to 2 Hz. Instruments such as LVDTs and strain gauges were used to monitor displacement and strain. The experimental results confirmed our numerical prediction, showing stable hysteresis with increasing damping as displacement increased. The VHD demonstrates consistent performance with negligible degradation after repeated loading cycles, proving its suitability and for real-world use. The Viscoplastic damper VPD integrates bent steel plates with visco-elastic rubber, providing both velocity and displacement-dependent damping. This design makes the VPD effective under both minor and severe seismic excitation, offering high energy dissipation. We tested the VPD under both harmonic and quasi-static cyclic loading. The damper showed a consistent energy dissipation, especially under large excitations. It outperformed conventional viscose dampers by a factor of 18.6 in terms of energy dissipation. The VHD was installed in a 3-story steel office building with 12 dampers placed in a diagonal bracing configuration. Installation was quick, taking less than 30 minutes per damper. The results showed significant improvement in the building's seismic performance. After the dampers were installed, the building's in-story drift decreased by 21.5% and its floor acceleration was reduced by 16.4%. This result demonstrates the effectiveness of the VHD in improving seismic performance without adding excessive stiffness to the structures. Here is a comparative evaluation of the VHD and VPD against conventional dampers. Both systems offer wide-range damping durability and low maintenance with cost-effective benefits. The hybrid design allows optimal performance across all seismic events. Our research led to the development and validation of two innovative hybrid dampers. The VHD and VPD systems combine the best features of viscoelastic and plastic damping mechanisms, providing effective, reliable, and cost-efficient seismic protection. Future work is focused on integrating these systems with smart monitoring of control technologies to optimize damping in real time. We also plan to scale up production and expand internationally for use in bridge, high-rise buildings, and infrastructure projects. In conclusion, hybrid damping systems represent the next generation of seismic energy dissipation technologies. These systems are reliable, cost-effective, and experimentally validated. Thank you for your attention, and I'm happy to answer any questions you may have. If you have any questions, please feel free to contact me at ahmad.modhej@gmail.com.